Okay, so this is the sequel to the last talk on MCSP. And let me just remind you, because not everybody was actually here, minimum circuit size, your input is a pair F and a number I, and you want to know does F have a circuit of size less than or equal to I. And there is a related problem that I spent some time motivating last time that uses a different notion of complexity. Instead of circuit size, it's a maybe unfamiliar, but nonetheless, I think, well-motivated notion of time-bounded Kolmogorov complexity, and here it's just the overgraph of that KT function. So you want to know if the time-bounded Kolmogorov complexity of X is less than or equal to I. And these are related because the time-bounded Kolmogorov complexity of a string X is roughly the same thing as the circuit size of X. And last time I gave history motivating these problems, but I didn't actually prove any hardness results. So let's start by proving a result that I just mentioned briefly last time, which is that graph isomorphism is in RP relative to MCSP. So if you've got a fast or efficient algorithm in some sense for this problem, among other things, you can do graph isomorphism with a randomized polynomial time algorithm.
And it doesn't matter which version of MCSP
It
you're using.
holds for MCSP, and it also holds for MKTP. It really holds for any reasonable notion. Okay, the central tool that we're going to use here is a fact that goes back to a very lovely, important paper by Hostad, Impagliazzo, Levin, and Luby, which is usually stated as one-way functions, which means cryptographically secure one-way functions imply pseudo-random generators. In this audience, I'm going to assume that you don't know anything about pseudo-random generators unless you all start screaming and waving your hands saying, we know all this stuff. So what is a pseudo-random generator? It's not the pseudo-random bit function on your laptop. From the standpoint of cryptography and complexity theory, a generator is just a function that takes short strings, let's say strings of length n to the epsilon for some epsilon, and produces a long string, a string of length n, or n to the k, where this is computable efficiently deterministically. So a polynomial time computable function. The input is called the seed, and the output is supposed to be pseudo-random. Well, what does that mean? It means that you shouldn't be able to tell, looking at the output, that it's not actually generated by something random. Well, what does that mean? You want to have the property that for every efficient test T, the absolute value between the difference, the probability over randomly chosen z of length n that t says yes, minus the probability over randomly chosen seeds s of length n to the epsilon that t on input g of s equals 1 should be small. And in different settings, small is going to be something different. But since I'm using a seed size of n to the epsilon, let's say it's less than 1 over 2 n to the c asymptotically for every choice of c. So polynomially close. What's an efficient test? It'll be something different in different settings. But it's just an algorithm, something that says yes or no. And if it behaves pretty much the same on truly random inputs as on pseudo-random inputs, then the test can't distinguish this output from truly random. And if this is true for every efficient test t, then this is a wonderful pseudo-random generator, because you just can't tell. Okay? So, if one-way functions exist, secure pseudo-random generators exist.
Is there a Kolmogorov complexity version of that?
In some sense, the whole thing is about Kolmogorov complexity. Well, the output here, it's produced very quickly from a short seed. So the output has got very small time-bounded Kolmogorov complexity. And so what that's saying is if these things exist, efficient tests, among other things, can't distinguish high time-bounded Kolmogorov complexity from low time-bounded Kolmogorov complexity. Or this should be hard, because the MKTP problem, what does it do? It allows you to tell the difference between high and low time-bounded Kolmogorov complexity, which is the point in some sense. This is a terrific test to distinguish the output of any efficient pseudo-random generator from random strings. Does everybody see that? This is the big hammer we're going to use over and over again for a little bit. And in fact, I mentioned last time, decades went by where people didn't see how to say anything about the complexity of either of these problems. And still, until a couple of years ago, the only tool that we had for reducing problems to MCSP or MKTP was this terrific hammer that's been given to us by de-randomization, namely this connection between hardness and pseudo-random generators. Did that kind of answer your question a little bit, or did I sidestep it? Okay. The intuition behind this, which is actually a quite involved theorem, but the intuition is somewhat easy. And we will be putting up a bunch of different theorems concerning pseudo-random generators, different types of constructions. But they all operate on the same general principle. If something is hard, then you can generate noise, which is what pseudo-random output is. And the intuition is pretty simple. If a function is really hard to compute, given x, you've got no idea what f of x is. It looks kind of random. And so the idea is to take this terrible intuition that if you can't compute f of x is sort of random looking, and you manage to turn it into something that's really a theorem. And there are a lot of steps along the way, but that's somehow the intuition.
The thing which satisfies the inputs.
The way we're going to use it is the contrapositive. So in fact, how do you prove something like this? Well, let's in fact state exactly how we're going to state this, the version. This is the informal version. Let f of xy be computable in time length x to the order 1. Among other things, this means that y is also going to be of length polynomial in x. Okay? For absolutely any L, any language L, for absolutely any BPP machine M, a probabilistic polynomial time machine M, for every L, for every M, for every polynomial P, there exists a BPP machine N, and there exists a polynomial Q such that for all n, for all y, if the probability that M on input L with on oracle L with input y are S equals 1. What's R? The length of R is just a string. R is just a length of a string of length to n, and we're also taking S, any random string. If that probability that M equals 1 minus the probability length x equals n and random bits S, M, L on input y, a particular generator that Hill tells you how to construct from f sub y. So this is f sub y of x. S equals 1. If that probability is big, this is terrible to read. What's this saying? If you've got a machine that can access L, L is this test, a test that's helping us distinguish random from pseudo-random. If with this test you can take, this is parentheses x, you can take the output of the pseudo-random generator so G f sub y Hill on input x, where x is a short string, a string of length n here. Instead of n to the epsilon here, we're going from n to 2n. If you can take a short string, a string of length x, feed it into the generator, and with input y telling you which function this was built from, and random bits feeding into M, if the behavior of this machine on pseudo-random inputs is different from random bits of length n, of length 2n, then the probability over random string x of length n and probability of s that f of y n with oracle L, y f of y x, comma s equals f of y x, that probability is greater than or equal to 1 over q of n. What is this saying? It better be saying that f sub y is not one way. And in fact, that's really what it's saying. Here, if you are given f sub y x, if you're given f sub y x as input, you can use this particular same oracle L that distinguishes random from pseudorandom, and you can compute something so that when I feed f with the same y there, it maps back to that. So in other words, it allows us to find something in the preimage of this string. And we can do this not all the time. We can't always find the preimage, but we can do it with reasonably high probability over a random string x of length n.
So this is going from in to it.
Yes. So usually these are actually equivalent notions, but here the generator is going from length n to length 2n. If you can do this, you can actually blow up any polynomial in polynomial time. That's not obvious, but it's true. Okay, so again, this is terrible to read, but I'm going to be wanting to refer back to it, so that's why I put it up there on the board. What's important for us is that this is true if you have any test. So here's a function f. There is a particular construction of a generator, g, parameterized by f sub y. And we build this pseudorandom generator, and if we have a test L that can distinguish random from pseudorandom, think of L as being minimum circuit size problem, or MKTP. If it distinguishes random from pseudorandom, then F is not cryptographically one way, which means that if you pick a random x and somebody hands you f of yx, this machine, which runs in polynomial time, has a pretty substantial probability of finding something that maps to fyx. You can invert it. It's not one way. So this is a funny sort of reduction. It reduces the problem of computing f to this problem L that's distinguishing random from pseudorandom. And that's exactly what we're going to use to reduce graph isomorphism. So how are we going to do this? Let G...
Sorry. So is that constructed?
Yes.
So there's a computer that's G is there's an algorithm which given L and blah, 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 will construct the G sub f of y from the parameters.
The Hill construction is extremely constructive. It's a black box that says if you've got Oracle access, if you've got a black box program for f sub y, it says, and you want a particular security parameter q, p, it tells you exactly what to do to compute this generator. And if somebody hands you an Oracle, L, well, in fact, forget about handing you the Oracle. The analysis gives you the program for this machine n. So we know exactly what n looks like. And we use that machine n to invert the function, and it just uses black box calls to this Oracle that we're using to distinguish random from pseudo-random.
Part of it is that this G is essentially a one-way function.
F is the thing that, so given any function f that's easy to compute, we can build a generator and, you know, in fact, the function we're going to use here is something that doesn't look like a one-way function at all. Let's be very precise. Define a function f sub g that takes permutations on the numbers 1 through n to the set of n vertex graphs. As follows, f sub g of pi is equal to pi of g. You just permute, you know, this isn't a pi here is a permutation, and we just permute, you know, output the adjacency matrix of G with the rows and columns permuted by pi. This does not, nobody would choose this as a candidate one-way function. On the other hand, this analysis works no matter what function we're going to use. So, in particular, to solve graph isomorphism, what are we going to do? On input G and H, we want to find out if G and H are isomorphic. Pick a random pi. So this is a probabilistic reduction we're doing. We're going to pick a permutation uniformly at random. And use let's say MKTP as an oracle to try to find a permutation, let's call it sigma, in F inverse, let's call it FG inverse of pi of H. F sub G is very easy to compute. Everybody agree that? F sub G is easy to compute, so this function works. Which means that this generator takes very small inputs and produces long outputs. And that means that for a pseudo-random output, it's always going to have very small KT complexity. I'm lying a little bit, but this is a technical thing. It's going to have very small KT complexity, whereas for a random string R, of course, it's going to be high Kolmogorov complexity. And so these probabilities for random strings, if we ask, does it have KT complexity bigger than n over 2, or let's say 3/4 n, the answer here will be yes with extremely high probability, and here the answer will be 0. The probability here, the answer will always be no. It's always low probability. So these probabilities are very far apart, which means that we can invert with high probability over a randomly chosen input. Well, we can randomly sample permutations, and thus, if G and H are isomorphic, this is a uniformly randomly chosen element of the range of F sub G, which means that we've got a pretty good chance of finding a permutation sigma such that if I permute G according to sigma, I get pi of H. If they're isomorphic. If they're not isomorphic, of course, I have 0 probability of that happening. And that's my one-sided error probabilistic algorithm. Okay, so this is a very simple argument once you've got all this fancy machinery.
It's somewhat similar to the Arthur-Merlin.
Actually, you'll see something that's much more similar to Arthur-Merlin later. But actually, I don't really see the connection to Arthur-Merlin here. Well, we're dealing with graph isomorphism, so permutations are going to show up. Yeah, I don't see the similarity here. Here we're just inverting a function. And we're using this high-powered machinery that says you can take any function that's easy to compute and from it build a pseudo-random generator such that if you can distinguish random from pseudo-random, and you can with MCSP or MKTP as an oracle, then you can invert. And it's crucial here that we be able to sample uniformly from the range, and everything else just works fine.
Well, what happens if you apply this to things that we think are one way, like say discrete logarithm, things like that?
Well, so discrete log, if you view it as a function properly, lies in the complexity class SZK, and factoring also lies in this complexity class SZK, and an argument fairly similar to this shows that SZK is contained in BPP to the MCSP or BPP to the MKTP. We can't get, as far as we know, one-sided error. We just get two-sided error. But the idea is pretty similar. And in fact, for discrete log and factoring, we can really do better. We can get that these are both in RP and, in fact, ZPP relative to MCSP because these have a lot of special structure. And if there's really interest, we can get into that. But right now, what I'm really trying to demonstrate is how this hammer of de-randomization works. That De-randomization tells us how to take a hard function and build a generator. And the generator is secure against, well, it fails to be secure against MKTP and hence MCSP because these are close enough to each other. And thus we can, because MCSP is a great test, we can invert the so-called one-way function and thereby compute F with high probability, and frequently that allows us then to solve a particular problem. In particular, what we're using here is the fact that given any pair GH, we can reduce the problem, are these isomorphic, to a question about inverting a function on a uniformly sampleable element of the range. Should I back up, or have I illustrated this point? Okay. So this is still about the best hardness result that we have for minimum circuit size, or MKTP. This is about the biggest complexity class that we know how to reduce to these problems. There are some crypto problems that are not known to reside in statistical zero knowledge, but and for those recently some reductions have also been found, but if you're looking for something like a complexity class, this is still about the best that we can do. So that is a hardness result. What I'm going to do, though, what I promised to do, is give you more evidence that MCSP and MKTP are not actually NP complete. And in order to do that, I'm going to have to introduce or reintroduce relativized versions of these problems. Now, when a complexity theorist starts talking about oracles, a lot of times you can just kind of turn your radio off, because it means that the complexity theorist is no longer talking about the problems you care about, but is talking about some alternate universe where you can actually get a theorem to go through. Here, though, we're actually using MKTP or an MCSP relative to oracles to give new examples of complete sets for complexity classes that we really care about. So let me remind you. Last time we introduced, or we mentioned Levin's KT complexity of X, which we said was about the same thing as minimum circuit size of X on oracle circuits that have access to an oracle from deterministic time 2 to the order n. And then part of the motivation for introducing K capital T, because KT of X was roughly the same thing as circuit size of X without the oracle. And that was part of the motivation. And so what am I going to do now? Well, I'm going to say this connection, KT relative to A and circuit size relative to A, that really holds for a bunch of oracles. And now I need to convince you, why do we care about MCSP relative to A. Number one, MCSP relative to A gives fundamentally different complete sets for complexity classes we care about, such as p-space, exponential time, non-deterministic exponential time, ... Basically, anything that's a big complexity class that you have a name for has a complete set of this form. Number two, we can answer some questions about MCSP relative to A that we can't answer about MCSP. And you can say, well, yeah, that's the usual reason that you introduce oracles. On the other hand, because of point number one, here at least it's telling us something about complete sets for classes we care about, and we can get some real answers. And we've got this gut feeling that the problem, the nature of the problem maybe doesn't change that fundamentally when you stick an oracle on it. You know, it's still high resource-bounded Kolmogorov complexity with some resource, and you know, how much does that really change things? Which, in other words, is point three. There's a chance this will help us understand MCSP without the oracle. And number four, tight connections to circuit lower bounds. What do I mean here? Recently, we have learned how to prove that the question, does this complexity class reduce to MKTP relative to A for certain reductions, is actually equivalent to the question, does the complexity class where A sits have small circuits? So we care about whether or not exponential time has small circuits, or we care about whether or not linear space has small circuits. And we will see that studying MKTP relative to various oracles A gives us a different way to understand the question, does this complexity class have small circuits? So we'll see how much of this we get to today. But part of this is predicated on me being able to generate interest in, among you, in different notions of reducibility. Because there are theorems that we will prove of the following sort. I'm going to reduce this, or erase this, except for the informal version. Theorem. MCSP on oracle circuits with a QBF oracle is complete for p-space, and MCSP with oracle QBF is not complete for p-space. So in order for this to be a theorem, of course, we're talking about different notions of reducibility. So if we want to understand what's going on, and we do, we need to convince ourselves that actually these different notions of reducibility are something we care about. So, what are the reducibilities that you know you care about? At least if you're here, you certainly care about polynomial time many-one reducibility. Everybody knows this notion, right? Do I need to remind anybody what polynomial time many-one reducibility? I got comments from a conference submission once complaining that I didn't understand, I didn't explain what this notion meant. Okay. If you're a recursion theorist, and you're not, an M reduction is just M reduces to B if there exists a computable function f such that x is in A if and only if f of x is in B. And the M stands for many because early on this was also studied in the context of 1-1 reductions. And this is a more general notion where they can be many-one. And mathematicians are extremely conservative, and once a notation has been used, it's there forever. Polynomial time, M reducibility, is the same thing, but now it's computable in poly time. And there's also the more general polynomial time reduction, A, polynomial time Turing reducible to B. And this just means that B can be solved in polynomial time. A can be solved in polynomial time if you have a magic subroutine for B. Okay, so many-one, Turing reducibility, polynomial time, these are our friends, right? But already today, I've had cause to use RP Turing reducibility and BPP Turing reducibility. And you all understood that this was a reasonable notion of reducibility, saying if B is easy, A is easy. At least gives you an efficient probabilistic algorithm. Okay, so everybody is comfortable with these notions, right? Stop me if I'm lying. Okay, that's because P is contained in RP, contained in NP, contained in BPP. RP and BPP are both contained in this class P poly. I think not everybody here is really comfortable with P poly, but I could be wrong. I'm going to define it unless you tell me that I'm wasting your time. Okay. What does it mean to say something is easy to compute? Well, the old answer is you've got a fast program for it. But an even older answer is that you've got a small circuit for it. But what does it mean to have a small circuit for a function? Well, if it's just a function on a particular input length, then it's clear what it is. It's a piece of hardware. But we're talking about functions defined on the set of all strings, which means that you've got to have a circuit family, a circuit for each input length. Now, if you've got a fast program, there are also small circuits, because you can implement, I mean, that's what we do, right? We take programs and we convert them into silicon. We can build circuits quickly from an efficient algorithm. But you can have an efficient piece of hardware for each input length without necessarily having any way to build the circuit. And that's what this class P-poly is. And you might ask, well, what use is that? Well, it would be pretty useful to know that satisfiability has linear-sized circuits, even if we didn't know how to build them, right? I mean, aliens could land and say, here, this piece of hardware would be useful, and it'll solve satisfiability on inputs up to 20 billion, and we could use that, and that would be useful. It's just asking what's the combinatorial difficulty of converting from input to output. So it's a well-motivated complexity class. Also, there's a very simple argument, which I can sketch to you over lunch, because a lot of people have seen it, of how to take a probabilistic algorithm and turn it into efficient circuits where we don't know how to build the circuits. So it's a class that does arise in various cases. And in particular, we will also need to talk about P-poly Turing reducibility. And these are all reasonably efficient notions of reducibility. You could also talk about P-poly M reducibility. For probabilistic M reducibility, it's a little bit more complicated. We won't be dealing with that. But we're also going to need to talk about smaller, more restrictive notions of reducibility. And that's because you yourself mentioned log space earlier. Lots of people in this room care about log space. Log space has also got complete problems. What's the notion of reducibility that you want to use for log space? Well, it's not polynomial time. It's not even log space. But log space is useful, and we will be needing to talk about log space reducibility, log space M reducibility, and log space Turing reducibility. This is useful for defining complete sets for P, etc. But there's also AC0 M reducibility and AC0 Turing reducibility. And I introduced these classes last lecture. AC0 is constant depth, polynomial size circuits. And as with other notions of circuit complexity, these can be either uniform or non-uniform reductions. And we'll be needing to talk about both versions.
So AC0, I'd say you'd have a typical oracle dice thing.
That's right. So here's an AC0 circuit. It's got inputs x1, x2, up to xn. It's got AND and OR gates, but also oracle gates. And in general, these oracle gates can feed in to one another. So we can have a bunch of oracle gates, and the outputs of them can feed into oracle gates at the next level. If that doesn't happen, if all the oracle gates are on the same level, then this is known as an AC0 truth table reduction, or a non-adaptive AC0 reduction. And we'll need this notion too.
But there's still a band on the depth of
Everything is still constant depth. The length of the path from input to output is a constant. Okay. So let's go back to these oracles. MCSP is complete for p-space under, it's actually complete even under RP or ZPP reductions, but what I'm just going to prove is an easy version. It's complete under RP truth table reductions. And it's not complete under log space Turing reductions. I think I'm only going to prove an easier version of that.
So is the second one under certain condition, p-space not equal to p?
No, this is a theorem. So we're using log space reductions. And log space
What is the difference between L and P? Because the
we don't know that L is different from P, but we do know it's different from p space.
What I'm saying is like this. So if P equal to p-space, then of course the problem is complete.
So for instance, here's something that's true, even though I'm not going to prove it today.
Yes, sure.
Now, we don't know if log space is different from ZPP. That's an open question. No, but we don't know if log space is different from ZPP, but we do know that the reducibilities differ. Okay, did everybody catch that distinction? In other words, well, in fact, this is in some sense almost trivial. So L, in particular to the MCSP QBF, is properly contained in ZPP to the MCSP QBF, which happens to be p-space. Now, without oracles, we don't know if L is different from ZPP. But with these oracles, we do know that this is a strictly smaller class. Did that answer your question?
Somehow, like a second one, you can see that. So if P equal to p-space,
If P is equal to p-space, then log space is different from P and
that would be complete, right? So that's what I'm saying. It's somehow like a difference in the reduction, and somehow the difference between P and L, somehow like that. Right? Somehow correct.
Okay. But all of the, every p-space complete problem that you can think of, except for this one, basically, is going to be complete under log space many one reductions. Okay? And so that's, earlier I said these problems give us fundamentally different examples of complete sets for classes that we care about. We care about p-space, and it's complete under a reasonable notion of reducibility, but it's very different than all the other complete problems that are even complete under this more restrictive notion.
So if we replace ZPP by P, is that a possibility? The first one still holds.
It's still a possibility. We don't know how to do that. I see I've already managed to speak for an hour. And I was going to prove this, but I'll prove it next time. And I will do some other amazing things next time, and we'll, so don't go away. Yeah. Okay.
So what is the MKTP? I'm just missing this problem.
Right.
Yeah.
So time-bounded Kolmogorov complexity of X is equal to the minimum length of the description. This much looks just like ordinary definition. Plus, we're adding the time t such that our universal machine given d and I gives us the ith bit of X. There's a little bit more, but so the reason why we allow I to be given as an additional input is because we want to have the running time be allowed to be a lot smaller than the length of X. And so here we're saying, okay, on this input that's just logarithmically big, tell me what a particular bit is. So if this description is enough that it can tell me, you know, we can get the length, we can figure out what X is, then this is a description, you know, a definition that turns out to be basically the same thing as circuit size. And MKTP is just the set of pairs xi such that kt of x is at most I. Yeah, except, you know, the history for MCSP, you know, it's got a long history of interest by people who were not particularly interested in descriptive complexity.